Hello, good evening, everyone. Am I audible?
Yes, sir.
Okay. Let's wait for a couple more minutes in case more students are joining, then we'll start. Okay. So we'll start now. So before we proceed for the revision session for MLT, um, which is organized to help you prepare for your quiz tomorrow. So before we proceed, any questions? Anybody wants to put in?
Sir, one area I like a little bit of understanding clarification is the normal distance from a point to the decision surface.
Okay, sure. So that will be covered. It's part of week 4.
Okay, sure.
So, Nitin, when we come to week 4, can you take up this one if you have not already prepared for it?
Yes, sir.
Okay. So we'll go week by week. We'll start from week 1 and then week 2, week 3, and week 4. This is the sequence in which we'll revise our content. So in ML techniques, week 1 is more of an introductory week in which Sir talks about the philosophy behind this course, how it will be conducted, why we are not using any machine learning libraries directly, and we will be focusing on mathematical concepts as well as the implementation of training algorithm from scratch. Then Sir also mentions how machine learning is actually revolutionizing many fields, how it is used, how it touches every human being on the planet. Then there is a very important concept that Sir explains is the 5 components of machine learning. So give me one moment, I'll share my whiteboard.
So would you be taking up the mock? There are a couple of questions wherein I have a doubt.
Can we take it at the end of the session?
Yeah,
Will
no
that be
issues,
okay?
sir. Yeah, that's right. Thank you.
Okay, is my screen visible?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay. So the 5 components of machine learning are. Can anybody would anybody like to volunteer for this?
Training data.
Training data, model,
Data. Then there is model,
loss
Loss.
function,
loss function,
Evaluation.
optimization. Correct.
and then evaluation.
Correct. So this is the framework which is important. So for any machine learning technique or algorithm, or any machine learning problem, these 5 components are there. If you don't have a data set, then there's nothing to work with. Then the model that we choose, the loss function associated for training that model. Then how do we train? We use some optimization procedure, and at the end, when we have a model, how we are going to evaluate it, how we are going to check whether it is going to generalize well or not, whether it is overfitting or underfitting. So evaluation criterion comes in. Now, the next point that Sir discusses is the taxonomy of machine learning problems. So we can broadly classify into 2: supervised learning algorithms and unsupervised learning algorithms. Of course, there are reinforcement learning and semi-supervised learning algorithms also, but we are not going to talk about them. They are not part of this course. For supervised learning, there are 2 types: classification and regression. So again, in classification, we can divide the problem into 2 types: single label or multi-label. Okay, before we do single label or multi-label, we should write binary and multi-class. So binary means there are only 2 classes, 0 and 1. There could be cats and dogs and things like that. But multi-classes, there could be more than 2, right? Or more. Then there is another classification of this, which is multi-label or single label. Single or multi-label. So the same thing goes for regression as well. So can anybody tell me difference between single label and multi-label?
Single
Multi-label.
label, in single label, we have only one option of final answer. For example, the same iris flower have there are 3 kinds of iris flower, but at the end, the flower could be of any one type. So this is single label.
Absolutely right. So flower classification is a single label, a multi-class classification problem.
But in a picture of fruits, if we want to say which fruits are there, so it can have apple, banana, grape, and all. So this is multi-label because there are different things which are possible.
Pardon me, can you repeat that part?
In multi-label, in a picture, if we have to opt for which fruits are present, so there can be more than one
Right,
fruit present.
absolutely,
It is multi-label.
absolutely right. Yes, that's multi. And similarly, this regression problem can also be single label or multi-label.
Sir, one question here.
Sure.
In binary class classification, can we have a multi-level? Multi-level?
Of course, we can do that. So imagine the same problem of the fruits, but you have only two fruits, mangoes and apples, in the picture.
Yes.
That's all you want to decide.
Okay.
So, questions so far? All right. So okay. So this is again divided into single and multi. Same is here.
Sir, one question here.
Sure.
Can you please give example single label versus multi-label
For regression or classification.
for regression?
Okay, sure. So for regression, let's say you just want to what will be the average temperature tomorrow, just tomorrow, next day. Okay.
Okay. And
Temperature.
for
Yeah, temperature prediction.
okay.
And what about you don't in multi-label? An example could be you don't want to just measure temperature, you want to measure the humidity as well. Imagine that. Okay.
Okay.
Temperature plus humidity. Right.
So wouldn't that be multi-class? I mean, I don't know. Temperatures for the next 5 days would be what then, sir?
Well, that could also be.
That could
So we
also
are
be
talking
multi.
about only temperature of next day, or we are talking about temperature and humidity of next day.
Okay. Okay.
Right. So
Yeah.
the set of features remain same for both the problems, but in the multi-label problem, the output will have multiple quantities.
Okay. Fine, sir.
So, sir, here if they will ask like let's say temperature or humidity, let's say temperature for next 5 to 10 days, then what
Okay.
will happen? In which section it will be? Single
It will
label or
still be
multi?
multi-label, right? Because each, let's say you want to compute the temperature for next 5 days, so there will be 5 quantities, right? Let's say 30 degrees Celsius, 31, 32, 32.4, something like that. There will be exactly 5 quantities,
Okay.
right? So you want to predict 5 numbers, not just single number, and that makes it multi-label.
Okay. And can you please give, I got confused actually with the classification and regression in this multi-level and single level. So it would be great if you can give example for that as well.
Sure, sure. So as somebody from the student group just mentioned that, so a multi-label example could be there's a picture, right? And in that picture, sorry, forgive me, forgive my drawing. You want to identify whether it is there is sun or not. Okay. So presence of an item. You can if sun is present, you can say just 1. Okay. If it is not present, then 0. Okay. So this is binary classification, whether something is present or not. It could be whether it is a cat or not, whether it is a dog or not. Okay. Now imagine a multi-label classification. What you want to do is you don't want to just predict what object. So you have 2 objects, not just 1. Okay. So in multi-label, what will be the situation? There will be one object sun. This is another object, let's say hills. Okay. So if it is this image is passed to again for this can be 0 and 1. This also can be 0 and 1. So instead of having just one label for a sample, for multi-class classification situation, you'll have a vector. Okay. So imagine if this picture is, is sent as an input for a single label classification problem. So either it is going to give you 0 or 1. Since there is sun, the output will be 1. Do you agree?
Yes.
Okay. But the same picture, if it goes through the second model, which tests for both items, sun as well as hills, it is going to give you a vector.
Okay.
Right. So single label, multi-label is just related to the number of quantities present in your output. That's it, output. If there is only one quantity, it's a single label. If there are more than one quantities, it's a multi-label.
Got it, sir. Pretty clear. Thank you.
Okay. Okay.
Sir, I have one doubt in multi-label. Sir, like predicting run made by Virat Kohli in next 10 matches.
Okay.
So, miss, in my opinion, it should be single label because in each match, Virat Kohli will make certain fixed number of runs.
Right.
And 10 matches will be the number of instances, means number of rows.
Right. Right.
But sir, in the one assignment question, it was labeled as multi-label problem. So that confused me. The goal is scored by a footballer in the next 14 match. That was also a multi-label problem.
Okay. 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 Right. So I think this question can be solved. Okay. Let me ask the question in a bit different way. The number of runs Virat Kohli makes in next 10 matches each. Now, is that a multi-label problem?
Next 10 matches each. I couldn't understand, sir. Each means.
So, right. So I just don't want the sum of the number of runs he makes in next 10 matches. I want the runs he makes in individual matches. Okay. So let's say we have Virat Kohli, and my question is, one is the number of, and we are considering only 10 matches. If you are considering 10 matches total, then again, it's definitely a single label problem. But if you are considering 10 matches each, right?
Okay.
Then it's a multi-label problem.
Then I understand, sir. Means in group, if it is a group of 10 matches,
right?
Then I can understand it should be multi-label problem. But sir, in the question paper, it doesn't mention all the time.
I see. So it must be clarified. But keep this point in mind: if each or every this kind of word comes in your question, that means it should be multi-label.
Okay, sir. Okay, sir. And one more thing, sir.
Sure.
Like run scored by Virat Kohli is a discrete number, isn't it?
Right.
So
yeah. Okay. Go ahead.
And we say that when the output is a discrete, then we tell it as a classification problem.
Right. Right. So imagine this. So your question is whether this problem should be treated as regression or classification, right?
Yes. Yes.
Okay. See,
run scored by or the goal is scored when the output is discrete, then also we say regression problem.
Right. Okay. Let me tell you why. See, when we talk about classification, let's say cats, dogs, and crow or pigeons, add a few more number of animals. For example, lions or elephants. All of them are not related with each other, right? They are different items. Do you agree?
Yes, sir.
So it's not like that if I add one or two through one to cat, then it becomes a dog. If I add one to dog, it becomes a pigeon. If I add one to pigeon, it becomes a elephant. There's no such relationship. Do you agree?
Yeah,
right?
Yes.
And whenever I say classification, okay, I always say that all the outputs or all the samples must belong to at least one of these classes. Let's talk about single level classes, single level only, right? Okay. Now, the problem with runs is, can you tell me what is the maximum number of runs a player can make?
Ideally, it should be indefinite.
Definitely. right? It's indefinite. There could be no balls, white balls, and keep this circle keep going, and the batsman can score many hundreds, many thousands of runs, theoretically, right?
Yes, sir.
Right. So for that reason, see, the function is increasing, like if it is for a continuous function. Again, I agree with you. Numbers can be cannot be fractions, but we pose it as a regression problem that makes more sense. All right. So the prediction of our output, we can just round it up or round it off and give it as prediction for runs. And in the output, there's a connection, right? See, 23 plus 1 is 24. 24 plus 1 is 25. So there is a connection between possible outputs, not unlike classification. Right?
So,
that's why posing it as a regression problem makes more sense rather than posing it as a classification problem. So even though it's a discrete numbers, but the function is the output function that you are predicting is not classification.
so means whenever we see the problem, then we have to think in terms of the whether the function is increasing or the kind of indefinite and the
right. What is the relationship between different outputs?
Okay, sir. Then this will help me to answer the questions.
Sure, definitely.
Yeah.
Similar things is you can ask a number of see, there are a few questions in which possibly it can be posed as cast. Well, any problem you can cast as a regressionist classification. That's not an issue, but it would make more sense. For example, just like this one, Virat Kohli, number of runs he scores in next 10 matches or next few matches, makes more sense to be cast as a regression problem rather than classification.
So something like asking whether how many runs Virat Kohli is likely to score in the next 5 matches is a regression problem, whereas how many centuries is he likely to score, whether he's going to score a century or not in the next 5 matches will be more a classification problem, right?
Absolutely.
Because centuries, you are just going to classify whether he's going to score or not, whereas
exactly.
The number of runs, if you're going to predict, that will be a regression problem.
True. Absolutely.
Right.
Okay. Thank you, sir.
Okay. Now,
sir, a related confusing statement that we had in one of the assignments is the average rainfall in the next 5 days, and I think that was ultimately it came out as multi-label, but I mean, at least I mistook it as average rainfall over the next 5 days. So
I see.
Maybe just in case such a question comes.
Okay, so if there is any confusion or chance of misinterpreting the question, we will deal with leniency. Maybe give it marks for everyone or add more possible answers, depending upon the interpretation. But the questions will typically be very clear, like mentioning average rainfall for coming 5 days each, or something like that will be there. So the distinction between single level, multi-level becomes clear. Okay.
Sure, sir. Thank you.
Okay, sure. Now, there is a very important diagram or concept that is covered in week 1. Is why do we need machine learning? So it's related to that concept. So in tradition and how it is different from traditional programming. So one question that's asked is we have an image in which let's say this number is written 17, and we want to identify via computer what this number is. And there's another question like 45 plus 23. What will be the output of this? So which one of them is suitable for traditional programming and which one of them is suitable for machine learning?
So 45 plus 23 is traditional programming.
Very nice. This is traditional approach.
Yes, and identifying the number of digit, it will be the machine learning problem.
Very good. This is ML problem. And can you also explain the reason behind it?
Sir, in the traditional programming, the mathematical models are already available.
Absolutely right. So this is that model which is already available.
Yes, sir. And in the machine learning problem, the mathematical model is not available. Output is available. and with the help of the output, we define the we what we say. I say search the model. Output will be the model.
Exactly. So we have input-output pairs, but we do not know the function which translates inputs into output. Right?
Yes, sir.
Okay. Yeah, absolutely right. All right. Now let's go to next part. So now we know that machine learning creates or tries to find out the relationship between mathematical relationship between input and output pairs. Then how that function is represented. Okay, so let's talk about linear regression, which is the main topic of week 2 and 3. So linear regression says any model, let's say we have a set of features, or before we do that, we have a data set. So data is represented as D as form of pair X and Y. So X is here our data, or I should say not exactly data, but input samples. And Y is corresponding labels. Right. So, for example, let's say you have a house price or no, house price prediction data set. It could be California or for some other state. It could be age of the house, area, right? Then it could be number of floors, and there could be many more. So this is just an example, right? So age could be, let's say, 21 years, area is 1200 square foot, number of floors is 1. There's another one which is very fresh, 5, area is, let's say, 900, number of floors is 2. Similarly, 10, 1800, the number of floors is 3. Imagine something like that, and there are prices associated with it. So let's say this one is around 10 lakhs, this one is around 20 lakhs, and this one was 30 lakhs. Right? So this becomes your label, and each of these columns will become features. Okay, is this clear?
Yes, sir.
Okay, great. So, but just by looking at this, you can actually, there's a direct mapping between X and Y, and this these set of numbers that we are seeing. So this will actually become your X, and this is your Y, and this forms your complete data set. Okay. So basically, what we say is X can have multitudes of features. X1, there could be X2, there could be X3, and possibly many more. And why? Since we are talking about only a single label problem, it will be just a vector with multiple values: y1, y2, y3 to yn. Represents the number of samples. Now we have a data set, and we have we have divided that into feature matrix as a label vector. Now it's time to come to our second component, which is a model. So first we'll talk about linear regression, how to represent a model in linear regression. So a model is represented with the help of certain scales. Okay, so what we assume is there is a in linear regression. What we assume is there's a linear relationship between input features and the predicted label.
Sir.
Yes.
Sir, one question with this notation.
Sure,
Here
sure.
you have written y subscript 1, y subscript 2.
Okay.
Should we write here y superscript 1, superscript 2? Because in notation you have written x superscript 2.
Right. Because see, each x1, x2, x3, they are vectors. And y under the subscript 1, subscript 2 are scalars.
Scalars, but y subscript 2 what is representing for first instance of data?
Sorry, can you please repeat your question?
Sir, y subscript 1 is representing label for first data set.
First sample.
First sample, and y subscript 2 is representing for second sample.
Right.
So I think, sir, if you have written here y x superscript, then we should also write y superscript.
Right. See, this does not represent one sample. Okay, let me double check if I am.
So that notation represents a data point, right? X superscript 1. That would be a.
Give me one. You are actually, yeah, you're right. So x superscript 1 represents. No, I don't think so.
Suppose, sir, for example, our model is y equal to w0 plus w1 x1 plus w2 x2.
Mm-hmm.
In that case, if we fit each sample in that model, then we have to write y superscript 1 equal to something that we x for each value.
See, I think.
Sir, if you write the model, I will be able to convey my points clearly.
Sure. Okay, so let's write our model. So model is represented by a weight vector. Right. So y prediction is equal to w0 plus w1 x1 plus w2 x2 plus w3 x3.
So
I see your point. Yeah, you're right. So this should be a sample. This should be representing a sample, right?
Yes, sir.
Okay. Yes, I agree. Okay. So in linear regression, this is how your model looks like. So this is your predicted output. And these weights, this correspond to your model. This regression problem is called, this regression modeling is called linear regression, because what you're taking is linear combinations of your input data or input features. And that is why, see, this represents linear combination. Not just that, I mean, taking along with the weight vector. So this and this is the reason it is called linear regression problem. Okay. So any questions so far? This is the model, how it looks like. Okay, great. Now let's come to the second part. Not the second part, third part. Once we have the data, we have the model. The third thing that we want to discuss is the loss function. So there is a quite much curiosity or confusion regarding loss function. So the sum of squared error is the variation of this we are going to use for loss function. Sum of squared error is defined as x w minus y, and that's it. So this x and w, this is your data set or training data, input samples we call it. This is your weight vector. This is the label vector associated with the samples. And what we do is we sum them. is equal to 1 to n, right? So maybe I should write or maybe I should write in a bit different manner. Right. So it should be xw minus y transpose xw minus y. So this is a vector notation. Another notation could be w0 plus w1 is 1. This is your I plus w2 is 2. This is your this much sample plus wm xm I minus y I. So this is your prediction basically. Sorry, this is your prediction, and this is the ground truth value or the label. You subtract it, you take a square of it, and you sum for all the values.
There is a half also there, right?
Not in SSE. I was coming to that point. So this quantity is exactly, I mean, taking the sum over everything. Forgive me. This quantity, right, xw is exactly represented by xw minus y in the vector form. So any questions so far? This is the standard definition of SSE.
Sir, but in previous quizzes, there are questions in which the half factor is also
good point.
For.
So please make note of this. We define loss function, which is JW, as half of SSE. So whenever you are asked to calculate the loss function, use this definition. Whenever you are asked to compute the sum of squared error, use this definition.
Okay, this is good clarification, sir. Otherwise, it is confusing.
Right, right. I understand your point. So see, we added this half only because there is this square and we are going to differentiate it, and this quantity will be cancelled out with half. Only for the sake of convenience, this half is added only. Yes.
Sir, can you please repeat? Please, I missed this.
Sure. So in the question or in the quiz, if you are asked to compute the sum of squared error, use this definition. Do not multiply it by half.
Okay, sir.
Okay. However, if you are asked to compute the loss function, use this. Then you do have to multiply half with SSE.
Okay, okay. Thank you so much, sir. Thank you so much.
Okay, sure. All right. Any questions so far? Okay. Now the next thing which comes in is, once we have the data, we have the model, we have the loss function. Now we need a optimization procedure, right? And by the way, why do we need an optimization procedure?
To get the best model, means to correct.
To minimize the loss.
Absolutely right. We want to minimize the loss, or so optimization and loss are very tightly connected. So imagine we have this kind of samples. Okay, so there could be so this is your X and this is your Y. There could be a possibility of infinite number of candidate models, right? This could be one. This is your, let's say this is model A. This could be one. This is model B, and this could be another one. Model. I shouldn't draw arrows. Just like this. This is another model C. Then there is this model, which is D. So we possibly could have infinite number of candidate models, and you want to choose the best one, right? So optimization procedure and loss function help us to do that. So loss function tells us how far or how accurate our model is making predictions. The loss function gives you a high value, that means it is making a lot of mistakes. The loss function gives you a smaller value, that means it's making a small number of mistakes. So this can help us guide, guide us to come to a very good model. So we can start with again. So if we talk about gradient descent, we can start with any random model. We can just try to go in the direction where the loss function is minimized, and we are happy. We can continue to do this until certain point, and whatever answer we get, we give it as the final answer. For regression, there is one more approach, of course, which is the normal method. So optimization for linear regression can be done in two ways. One is normal equation. Okay, and the other one is gradient descent. So we'll talk about that. So do you want me to derive it, or should I directly write the formula for it?
I think so. We do not have too much time, sir.
Yes, sir. Directly write the formula.
Okay, sure. Sounds good. Okay, so okay, so our equation looks like
W is equal to X transpose X inverse, right?
Right.
X, Y.
X transpose Y.
X, Y.
No, X transpose Y.
X transpose Y.
True. Yes. Yes. Thank you. So if you ever want to learn a short trick of remembering, just start with this. This is what you want to achieve, right? Then multiply it. Since we cannot take the transpose of X all the time, so what we do is we multiply. Sorry, we cannot take inverse of X all the time. So if X were square matrix and didn't have any, its determinant is also not 0, you could have directly written something like this, but that's not the case. Many more often than not, the number of samples are much higher as compared to the number of features. This is gives you X transpose Y, and then you take the inverse of this and multiply it the other side. Okay, just a side note.
So is this why when we use the direct NumPy function, right, the pseudo inverse function, we directly just do inverse of X and multiply by Y, is it? That's why we do that. We are not doing this X transpose X inverse X transpose Y. I mean, at least in the functions that we have done.
Right. So the pseudo inverse computes the inverse of this guy.
Okay. Okay, so therefore we just do a NP lineage pseudo inverse of X and just matrix multiply with Y, and that's it. That will give me the normal.
Exactly.
Okay.
True. So see, compare these two equations. These two equations. So the left hand sides are equal, and if you remove the Y, the X inverse. Again, I shouldn't write exact equal. This is not mathematically equal. So this is pseudo inverse. If X is not inversible matrix, then it's a pseudo inverse comes out to be this much. And that's why in NumPy library, when you do the inverse of X, this is the quantity it computes.
Okay.
Does it make sense?
Yes, it does. Thank you.
Okay. So this is your normal equation method. Now we come to gradient descent. So in gradient descent, we have. So first, I'll just tell you briefly its concept, what gradient descent is. So imagine that you have a very simple problem in which there's one feature and one sample. Sorry, not sorry, one feature and one label. So you have just one vector for x, one for y. Your w will definitely have two quantities, w0 and w1, after augmenting the right after augmenting your dummy feature. Then in a situation like this, you will have a loss function which has two parameters. W0 and 1. In such case, you will have a 3D diagram. A bowl-like shape, a 3D bowl, of course, where on the z-axis you have JW, which is loss. On x and y axis you have W0 and W1. And now you want to choose. Now you start with a random point and you want to choose to a point where the loss is minimum. That's our goal. So that's how we say that our model is best fit or not. So start with any random point, and any random point in this loss function belongs to a model in the input space. So let's say we start from here. We start from here, and what we do is, so the concept goes something like this: we compute the gradient at this particular point, and it will come out to be in this direction, right? So whichever direction it is pointing to, we take the step in the opposite direction, which is this one, right? So that's where our minima lies, towards the opposite direction. If we keep going in the direction of gradient, instead of converging, we'll diverge. So this is what we do. So JW is actually we differentiate JW with respect to W. So this gives us the gradient. Okay. And what we do is we subtract this from W, but before subtracting, we multiply it with alpha, which controls our step, how fast or how slow we want to go towards the minima. This is your old W, and this should give you W. So this is the formula for one iteration. Is this clear?
Yes, sir. Yes, sir.
Okay. Okay. So now what will happen is if you start from this point. Okay, I'm going to draw a slightly bigger diagram, bigger curve, just for explanation. See, okay, so let's say you start from this point. Since the gradient is very high, I mean the magnitude of the gradient is quite high, you're going to take a large step towards the minima. So it will come out to be something like this. Then let's say you end up over here. Then since the magnitude is smaller over here, so you're going to take a smaller step. Let's say end up over here. And same thing, you keep doing until you see that your loss function has stopped reducing. So the later steps will be definitely smaller than the steps taken earlier. And at the end, after the training, you will end up over here. And that's the point where the loss function is minimum, and that corresponds to the final W, the weight vector you receive, which is your answer, which represents your model. Any questions?
Sir, what are here W new represent? W0 or W1? Is it a vector or is it a scalar?
Good point. So this formula, W is a vector.
W new and W old both are vectors.
Absolutely.
Sir, a similar thing in Perceptron for classification, we use plus alpha del JW by del W. Is that because it is using a sign, it is using a function?
In Perceptron, the Perceptron training model is not based on derivative, right?
No, yeah, it is a function basically. It is the yi minus y hat into the function of w, x, sorry.
Okay, okay. So, okay, I understand your point. So, in Perceptron model, what you do is you take every misclassified point and figure out how much you want to change your vector, right?
Yeah.
Your weight vector. Right. Okay, so can you wait till week 4 comes up? We'll discuss.
Yeah, no, it's okay, sir. I'll wait. No problems. I just had a confusion when I was going through all the slides. I mean, I found out this difference. So that's the reason I picked it up now. Yeah, you can clear it later.
Okay. Okay.
Yeah, thank you, sir.
So continuing from this point, there's another method to write this update formula. We could have written it for individual W's as well. So let's say this is Wi, and this, or I should write dash, which is a new version of it. This is Wi old minus alpha del JW divided by del Wi. So what I'm doing in this formula is I've isolated just one weight value and I'm trying to update that alone. So if you look at this formula, some time back, where it is, loss function, yes, there it is, this formula. Right now, the value of writing half comes to life. So when we differentiate this quantity with respect to any Wi, this half, the 2 will come forward, will be multiplied, and this half will be cancelled with that 2. Okay. So that's the reason for convenience. Now your formula would look something like this: Wi minus alpha times W0 is W1x1 plus W1xm multiplied by x of I. Is this clear? Why is it coming out of this? Hello, am I audible?
Yes, we have differentiated the loss function.
Exactly. I have differentiated that SSE, and of course there was half over here, and then the 2 that came from over here was also there. It got cancelled, so I skipped that step and that will run this.
Sir, another question. Should we also write summation after alpha?
Of course we should do, because you want to do it for all the samples, right?
W1 minus, yes, sir.
Okay. So good point. We definitely should write W when we're talking about individual weights inside weight vector. Okay. Now the last part which is remaining is the evaluation part for a linear regression model. Now you know what kind of data is used in linear regression, what is the model, what is the loss function, how do we optimize it. We discussed both of them, gradient descent as well as normal equation. The last part which remains is evaluation.
Sure, sir, one question.
Sure.
Sir, method of normal equation seems to be easy. So why one should choose gradient descent algorithm?
Sorry.
Normal equation method seems to be easy. So why one should choose gradient descent algorithm?
Fantastic question. Amazing question, actually. Very good question. If we already know a very good solution, analytical solution, it is going to give us the correct answer all the time. Why do we need gradient descent algorithm at all, right?
Yes, sir.
Because let's say we stop in 4 or 5 iterations, or not large number of iterations, it is going to give us a suboptimal answer, right?
Yes.
Okay, fantastic question. Now imagine let me ask you this question. You have a data set. There are let's say 10 billion samples and a million features. Yeah, not bad. Imagine just this. Okay, so you have a 1 billion features and 1 billion samples and 1 million features. So what will be the size of your feature matrix?
1 billion sample.
Right.
So 1 billion into 1 million.
Oh, absolutely right. So 10 per 15. Do you agree? Okay. And let's say each entry, for the sake of simplicity, we assume that each entry takes only 1 byte. So these many bytes will be there.
Yes.
How many gigabytes is this? Okay, so let me help you with this. 10, whatever this number is, 10 per 15, 104. If I divide it once, it gives me kilobytes, right?
Yes.
Divide it twice, it's going to give me megabytes. If I divide it thrice, it is going to give me gigabytes. So it's roughly again, 10 per 15 divided by 10 per 9. So I just substituted this with 10 per 3. Okay.
Yes.
This is 10 per 6 gigabytes. It's huge amount of storage. Even if I reduce 3, this instead of making let's say 6, if I make it lesser than that, let's say if I make it 2. Okay. So that this turns out to be 100 gigabytes. Okay.
Yes, sir.
So if you want to apply the normal equation method, you want to load the entire data set into memory. So you need a memory of this order, RAM, which I say. Okay.
Yes.
Now you can imagine that a normal person doesn't have access to a huge server or a supercomputer which could possibly have memory like this, right?
Yes.
And again, I've just diluted the example. If you imagine the scale of data that big companies like Microsoft, Google, Amazon, they will have even higher amount of data, much higher order of data. So Google and Microsoft, they kind of add 1,000 servers a day, something like this. They acquire this much amount of data. So if they want to apply linear regression, it will be impossible for them. Right. And for anybody who has limited amount of RAM or primary memory RAM, then they cannot apply normal equation method. So even if you have data, let's say 60 GB, in modern standards, it's a not a big amount of data. But let's say your machine has only 8 GB of RAM. And if you work with a, I should say, linear regression problem, apply normal equation method to solve it, your machine either will hang up or it will take, I don't know what will happen. But definitely you are not going to get your answer very soon, or possibly not at all. Does it make sense?
Yes, sir.
Okay, that's why we need gradient descent. So gradient descent, of course, you have to run it many numbers of time. many iterations, and also at the end of let's say running it for 1,000 iterations or 2,000, 10,000, a million iterations, you are still away from your optimum. It is possible, right? But it is going to give you a workable solution. So that's a trade-off we make. Okay. Hello,
Sir,
this
one
makes
question
sense?
about gradient. Yes, sir. Sir, one question about gradient descent algorithm. Suppose, sir, we are getting a minimum value at 86th iteration.
Okay.
But we have already defined f(opt) value to 100.
Okay.
So in that case, we are going to iterate up to 100 iteration.
Okay. Okay.
So we are not getting here the minimum point.
No, you will get after 86th iteration. You are saying that after 86th iteration, the loss value becomes 0 or lowest, whichever the case.
Yes,
And you're saying the next 14 iterations are waste, is it?
Yes, sir. Because we have set f(opt) value to 100.
That is fine. The gradient will be 0 at that point, right? Or very close to 0. See, if you reached a point which is, something like very, something over it. Let's say this is your optima, okay? But
Yes,
somehow you reached only, I'm going to enlarge it even further. Let's say you reached over here. So what will the magnitude of gradient? Very, very close to 0. This is your answer. This is your answer. The gradient at this point will be very, very close to 0. So your number of steps, 14 steps will not be, I would say not 8 steps. It will make smaller problems. Okay. Now coming to the next point. So it was a great question that why do we need gradient descent? That's why I went 2 minutes and we'll talk about it. Let's talk about the next component of the machine learning, which is evaluation. Okay, so one of them is squared error, but we don't use it quite often. Instead of squared error, we use RMSE, which is exactly equal. Okay, so somebody can someone tell me why RMSE is preferred over SSE?
Because sir, SSE grows with the number of sample or number of examples. If there are more examples, SSE will be more. Exactly. So we cannot compare a model based on that. Whereas RMSE takes the average first, then it proves it.
Okay. So what about if I just take the SSE?
Kind of standardizes it.
In the same units as the
exactly
data itself.
That is also
exactly.
Yes.
So RMSE is the same unit as label or input.
Labels, sir.
Exactly. It's the same unit as label. So what happens is, let's say your RMSE, imagine your RMSE comes out to 1.2, and you are measuring again prices of houses. So you can say on an average your model makes 1.2 lakhs of mistake per prediction. Okay, so this becomes more interesting. That is why RMSE is preferred. Okay. Any questions so far? All right, great. So one concept that sir explained in these slides is the special point about alpha. Alpha is your learning rate, and choosing your learning rate appropriately can actually make a lot of difference in your training process. So sir considers 3 possibilities of your alpha. So one is, let's say it's very, very large. Let's say it is just just right. And let's say it is very, very small. So what kind of behavior you are going to see in your training session when you are using alpha very large, just right or small? That is what also been covered in the content. So can anyone tell me how it look like for just right, large and small? So imagine on the y-axis your there is loss function JW, and on your x-axis we have alpha.
So for the large, you can't really say, right? Because it might bounce off.
Yeah,
large will increase. The loss will probably increase. So
absolutely right. So
the learning
instead
curve
of
will be the other. Yeah.
absolutely right. So instead of decreasing, the loss function might increase, and that is bad because instead of training going towards the optima, our optimization procedure is going away from the optima. So this is bad. The second one is just right, so it should look something like this, right? And for a small, it is going to make. Anybody wants to say?
It won't go. The loss will not reduce after a certain point. The loss will remain high. So the curve will peter off at the high loss.
Or you can also say that the loss function is going to decrease very, very slowly. It is going to decrease, but very, very slowly.
The x-axis should be number of iterations, right?
You're absolutely right. Yes, I made this mistake. This should be number of iterations. Number of iterations. Right, this is how it should be. So the number of epochs is increasing definitely. So as you move with your training, as you go from one epoch to the other, this is the effect you are going to see if alpha is set to be large, just right, or small. So keep this point in mind. Okay, any questions so far? All right. So let's talk about the other part of linear regression, which is polynomial transformation or polynomial regression. So so imagine this kind of data set that we have. I'm just going to take it from the book itself or the slides.
Sir, sorry to interrupt, but before going this, like, are we going to discuss SGD once? Because I wanted to like clarify a doubt in that.
Sure. We can do that.
So in the SGD, this, the way that sir coded it, he was decreasing the learning rate every iteration, but actually that is decreased every epoch. So in the code, like, so like what really is like the right implementation?
See, the vanilla version of SGDs, you don't change your learning rate at all. You keep it fixed. But for creating the collabs and the diagrams that we use in the slides as well as collabs, we adjust as a learning rate.
Then that I understand, sir. Sir defined a learning schedule, but that learning schedule was decreasing every iteration, like for epoch in range of epochs and for I in range of data points. So in the second loop, it was decreasing like every time. But actually in the SGD implementation, that is decreased after every first loop, like for epoch and range of epochs.
So you're saying is that, so even before one epoch is complete, for every sample, the learning rate is decreased, is it?
Yeah. But in the actually the sklearn implementation, it is decreased after every epoch.
Okay. So I would say that is fine. That is okay. So learning rate, if you look at the implementation that sir used, it is reducing very, very slowly, not fast. Okay. So why do we want to, okay, before we dive into this, can you tell me why do we want to reduce the learning rate for SGD?
Because SGD bounces a lot at the start. So
Right. So as some number of iterations and epochs are done, what we want to do is we want to reduce it so that even if it jumps, it stays closer towards the minima.
Yeah.
Right.
Yeah.
Yeah. So that's only an implementation detail. I would say updating your learning rate every epoch or every iteration. That's fine. Both of them will work.
Okay. Yeah, they both work, but I was just like trying to clarify because one will converge a lot. Will take a lot of time to converge than the other.
True. True. Which one do you think is going to take more time?
The second, like if we keep it inside the second for loop, because that would really decrease the learning rate a lot. Like.
Right. Right. So is your question clear?
Yeah. Yeah. Okay.
Okay. So there's an important part, of course, SGD, MPGD, and batch gradient descent. So I'm going to briefly tell everyone about what they are. So in batch gradient descent, and sometimes only called gradient descent, every epoch is, every time we update the weights after going all the data samples. So n samples are used to update the weights, update W. In MVGD, let's say the entire n data set is divided into k batches. So we update weights every batch. Okay, so let's say there are 1,000 samples and there are 10 batches. So when the gradient descent is has gone over all the samples, it must have updated the weight vector 10 times. Okay, and SGD is stochastic gradient descent. Even extreme version of MPGD where k is equal to n. Right. So there are exact. So k here is number of batches. Remember this point. So k is equal to n. That means there are n number of batches, and every batch has only one sample. Is this clear? Any questions so far? Okay. Now let's proceed to the second part, which is our polynomial function.
Just a clarification. So k is the number of batches, right?
Right.
So this is basically n by k. We are saying there are 100 samples we are doing every batch.
If k is equal to n, every batch we are doing one.
No,
in this one.
Example above, right?
Yeah.
So you are doing 100 samples every batch.
Right.
Right, sir.
Okay. So now come to the second part, which is polynomial. So imagine that you have this kind of data set. Now, looking at this kind of data set, is the need for. So the ideal model should be something like this, right? But your if you apply the technique of linear regression without any polynomial transformation,
Swarnim, how you are defining the ideal means, is it the number of cards or the nature of the card?
Ideal means it is going to provide you lowest loss, not underfitting, not over. Nature of the curve also. Right? If you look at this curve, you will see that there are two inflection points. Right? So if you just apply linear regression, you're going to get a curve like okay. And if you use what should be more appropriate model for this, right? Do you agree with this? Hello.
Yes, got it. Thank you, Swarnim.
So now what we want to do is, if the data itself has a non-linear relationship, then we need to make our model more complex so that it can capture these non-linear relationships. For that, we use polynomial. So polynomial regression has components. Just polynomial transformation, plus linear regression. So how do we? So this part we know already. This is the only thing. This item is a new item which. So I'll tell you what. Polynomial transformation is transforming our features to get polynomial new features of different polynomial. So for example, let's say you have features x1, x2. Okay, again, imagine these are. Okay. So after just adding your dummy feature, this is how it looks like. X1, x2. But again, this is we want to make our model more powerful so that it can capture. So we wanted to transform it for degree. So we wanted if you also wanted to increase its capacity, let's say not just degree 2, degree 3 as well, then we have done something like this. And so on. You can keep moving. Now what will happen is this model can capture data sets where the underlying model is represented by a polynomial function of degree. This can easily capture. Of course, it can capture for degree 2 and degree 1 as well. But we'll come to that point where what happens if the underlying data set is here, and let's try to fit a model with a very computer. So the data set we were talking about was something like this. Now you can see that it has 2 inflection points, can easily be represented by a function. So if you start with this model, this transformation, and then choose complete variable. So normal equation, your model would put something for sure.
Excuse me, sir.
Your voice is breaking a bit. I mean, I don't know if I'm the only one.
Your voice is breaking, sir.
Okay. Is it better now?
It sounds better. Maybe you'll have to continue talking.
Yeah, when you continue talking, then it breaks up in the middle.
Okay. Then I'll speak a bit slower.
No, it's better now.
Okay, sure. So what I was saying, that if you if these were your original features or something like this, and then you had applied third degree transformation, this is how your input feature matrix would look like. And the original problem that you are talking about, which we saw like this, the data points are represented by x's, small x's. And if you had fitted a model with degree 3, then you would have definitely received a model like this, which is shown in the picture by red line. Any questions so far?
So what do we consider as a smooth fit?
Fantastic question. I was about to come to that. So now when you have a data set, you do not know what polynomial transformation will work the best. So what you do is you try to fit your model with different degrees. So imagine you get a graph like this. So here is your RMSE and here is your degree. And you want to choose the best value of the degree for the particular model or particular data set. Okay. Now, the training loss or training RMSE will definitely decrease with increasing the number of degree. So it would look something, let's say, like this. Then here it is. It is going even lower, lower, lower. Because let's say if we talk about only this data set itself, you will see that if degree 3 polynomial is doing this, if I fit a degree 6 polynomial, it is not going to do, it is going to do similar fit or even better because it has more complexity. Some of the places it will reduce the error even further. Maybe I should have taken a more sparse data. So imagine this. So this is your, these are your points. This is how it looks like. So this might be a very good fit. However, this might be an overfit. Do you agree?
Yes, sir.
Right. So this model A is just about right. This model B, forgive the colors, it's overfitting. The reason for B to overfit this data set is degree for B, I should say degree for B is much higher than degree of A. Right. So what could be
Sir,
yes.
is this always the case? Like, if we increase the degree, it will always fit the model much better. I mean, training set much better, regardless
Yes.
of how the training set looks like.
See, regardless of I can give you an example. Let's say there are n samples. Okay. Then give me the degree for which your model is going to give you 0 training loss.
Sir, how do I know that?
Infinite.
Okay. Let me ask you this question.
Okay.
You have
yeah.
you have 3 samples, x1, y1. Just imagine coordinate geometry. x2, y2, x3, y. Okay. And these are numbers basically, just 1, 2, 3. Right? I have these 3 points, and I want to create a function which passes through all these 3 points. How can I do that?
If it's in a straight line, it will be linear fit. If it's not,
So they are not. Let's say they are not linear. They are something like this. 1, and the loss function is 0. I want to create a function which goes through all 3 points.
Degree 2 metal.
Hello.
I guess, sir, we have to make the model as such that it passes through all the 3 points.
Yes. How can we do that?
Like a degree 2 polynomial.
Exactly, degree 2 polynomial. Then how can we do that?
Like we could just, for this example, you could just draw a parabola passing through these 3 points.
Right. So what I can do is I can just assume that my is ax squared plus bx plus c, right?
Yeah.
And put all these 3 points and solve it. Correct?
Yeah.
Similarly, if let's say there were 4, there's one more. Or it could be on the parabola itself. But imagine that it is here. Then
Degree 3 will work.
degree 3 will work, absolutely. So ax cube plus bx squared plus cx plus d will be your function. And you solve this, and you are going to get loss 0. You're going to get a function which passes through all the points. So what I'm asking is, let's say if I have n samples and data points, what degree function will pass through all of them if I'm trying to represent my model with a polynomial function?
n-1.
Yeah.
Exactly. So degree will be n-1 if I, again, try to create a function something like x is for n-1. This is my constant c1 plus c2 x is for n-2 up to the final term will be, let's say, constant bcn multiplied by x is for 0.
But sir, can this be, sorry to interrupt, sir, can this be generalized? Because had that x4, y4 been on that parabola, we needn't have a cubic polynomial, right?
Absolutely right. But let's say they are not on a parabola. They are, then you would have to take a polynomial of degree 3. It is going to definitely fit, right?
No, sir,
if it is on parabola, then it is going to possibly this quantity will be 0 or something that will happen, which will tell in the function that maybe we don't need a 3rd degree polynomial, even 2 degree polynomial works, right?
Yeah.
But maximum a polynomial which can the maximum degree of the polynomial which can easily go through all 4 points is represented by these, right?
Yes, sir.
Similarly, if I have n samples, the maximum degree of the polynomial which is going to go through all the points is given by something like this, right?
Yeah. It could be the maximum degree actually.
Right. Even if I get further, that's not needed.
Yes, sir. Yeah.
Okay. So if I choose a model like this, I can easily make my training loss 0, right? So if I keep increasing my degree, I am definitely going to decrease my training loss. You see the point?
Yes, sir.
Okay. Now, that's why when we increase the degree of the our model, it is going to become more complex, more powerful, and also it will also try to not just learn the pattern inside the data, but the noise as well, and that's something bad we don't want. Now this is how your let's say training loss looks like for different degrees. And see, so now after this argument, we can say that for any data set which is n samples, n-1 is the degree of polynomial transformation which is going to give your training error 0. But that's not what we want. We want our model to generalize properly as well, right? So imagine this is your training loss, and this is how your validation loss looks like. Something like this. 2 just go over here. 3 is still decreasing. For 4 it is increasing. So validation loss looks something like this. Now, whenever you are stuck in this kind of situation, and you will be asked a question like, which degree do you choose for this data? Which degree of polynomial transformation is best for this data? Which one would you choose?
3.
3, of course 3. Because for 4, even though training loss is decreasing, but the validation loss or test loss has started to increase. So that's definitely what we want. So we just look at the validation loss, whichever value of the degree is going to give us the minimum validation loss. Of course, along with training loss, that is the one we choose.
Sir, but is there any difference between a smooth fit and an optimal fit?
No. In the slides, they are being used interchangeably. So yes, whenever we say that 3 is the best one, so related to 3, degree 1 and 2 are underfitting, and degree 4, 5, 6 are overfitting. This is what we say. Does it make sense?
Yeah.
Okay. So yeah, there are questions like that in practice and graded assignment. So please make note of that.
Sir, so just now you said 1 and 2 will be underfitting. So even if they are very close, they will still be underfitting, right?
Relatively speaking, yes.
Okay.
So can anybody tell me in a single line what are the symptoms of underfitting?
Both training and
So
the
both training and validation loss is high.
Absolutely right. And what about overfitting?
Overfitting, the validation loss is high and the training loss is low.
Absolutely right. Yes. So keep this point in mind. This concept on this the 2 lines that you just mentioned, they are applied for classification as well.
Sir, the red curve that you have drawn here for a validation curve. So is it always the case, or you are just assuming here that a validation curve will be like this?
So for this data set I was talking about.
For this particular data set, you are assuming that validation curve will be like this.
Your curves would look like something like this.
Or in general, this curve will be look like this, or this is only particular for this particular data set?
See, again, I have taken hypothetical example, but of course you can try with higher number of polynomial degree. For large data sets, it becomes a bit difficult to do the experiments. But yes, in general, you can see curves like this. Sometimes the validation loss might not look exactly like this. It might fall off later as well.
Okay. So when we are generalizing this this statement that overfitting will be in the case when validation loss is high and training loss is minimum.
No.
Yes. Means we are generalizing this curve, no?
See, when you say that training loss is low or validation losses are high, it is not just related to polynomial transformation. It is related to every supervised learning.
Oh, okay, sir.
Okay. Now, the next point is, let's say, looking at the data, we do not know what degree should be suitable, and it is possible that we might overfit. So, in this example where we saw that 4, 5, 6 degree polynomial transformation model is going to overfit our data. So, how can we take care of this? Can we penalize this in some manner whenever the model is overfitting, and hence comes back to a better set of weight values? Can we do that? So the answer is yes. So first I'll talk about the ridge regression. So this is how our model is represented. XW minus Y transpose X, oops, should be U minus Y, half of it, plus, can we put some kind of penalty over here so that every time our optimization procedure tries to overfit the model, it pulls it back. It doesn't allow, that penalty term doesn't allow it to go in the direction of overfit.
Regularization rate.
Exactly, regularization, which is num by 2 transpose W. Okay, so before we move forward, why do we do this? So this is basically second norm of W, right? So why do we? So basically, what we are saying by adding this penalty term is whenever the values of individual weights or parameters inside the weight vector are increasing, add the value of that into your loss function so that it does not do that. This is what we are saying. So this, by adding this quantity, we are forcing our optimization procedure to not let the individual weight parameters W0, W1 up to Wm to go to acquire large values. So we are forcing these to remain small. Can anybody tell me why this is going to work?
Sir, because sir, as the model tends to overfit, this W0, W1 up to Wm, they also tend to grow.
You're absolutely right.
So if we add them to loss function.
Absolutely. So this is the observation. So whenever a function has too many fluctuations or curves, you'll notice that the values of these individual weight components will be very, very large, and that's what we want to do. So that's a sign of overfitting, another sign of overfitting, and what we want to do is we want to make use of that. So whenever so what we do is whenever optimization procedure tries to increase the weights of W, this quantity is going to pull it back, because instead of going so let's say our optimization procedure, just by looking at this first item, goes towards the overfitting direction. That means W's are growing or increasing. This penalty term will say, okay, if you increase it by much, I'm going to add a penalty. So instead of increasing the loss, it will instead of decreasing the loss will increase. Hence, this penalty term is going to prevent from overfitting our model.
Sir, but the weights of all the weights are not high, right? Like only the polynomials with higher degree, they have higher weights.
Okay. Right. So what we want to do is we don't want any weight to all weights to be considered equally. We don't want any particular weight to dominate.
Yeah.
Right. So if you write this, even the coefficients of polynomial terms are also not allowed to increase. Do you agree?
Yeah, because they act like weights, right? Weights are the coefficients.
Right.
Sir, Miss Kisar, that W0, W1, W up to Wm, this is a vector quantity. And W transport W is a scalar quantity.
Right.
So, sir, how this scalar quantity will control the vector?
Good point. See, so when you differentiate it, it is going to become a vector, right?
When I will differentiate W transport W, it will become
a vector, yes.
Okay.
It's just be lambda W then.
Exactly. So if I differentiate JW with our W, I'm going to get an equation like this. This is your lambda. Okay, so this is a, again, you can verify that this is a vector of size, I would believe m by m, m plus 1. It would have m plus 1 components. This is going to get m plus 1 components. This is X transpose. That means m plus 1 by n. This is going to be prediction, which is n by 1. Right. And if these two matrices are multiplied, this n will be eliminated, and you are going to get m plus 1 vector, same size as this one. Is that clear?
Yes, sir. Yes, sir. Clear, sir.
Okay. So this is for ridge regression. There's one more type of regression that you can do, which is lasso. And in that, your loss function looks something like this: half of xw minus y transpose xw minus y plus lambda by 2 as it is. But instead of second norm, we use first norm of w.
Sometimes this is confusing. So when we say norm of W, right, usually it means the length of that vector, which is square root of the components of the vector. But here we are actually doing absolute of the vector, right?
Right.
So first norm is just absolute of that vector, is it? That's what it means.
Exactly.
So is it absolute or is it the root of the W transpose W, right?
No, it is not root of W transpose W. So let's say if your weight factor is for at any iteration or beginning of the training, which is let's say 1, minus 2, 3. This is your weight vector. Okay. So your W1 norm will be just 1 plus mod of minus 2 is 3. Mod to be 6.
Okay. But I've been doing the root and I've always been getting the right answer, sir. I've been doing the root of W transpose W.
No, how? It's
I wonder how.
That is for second norm.
The second norm will be no square root.
Yeah, second norm will be no square root, and for the first norm, I've always been doing the root of the second norm.
No, they're
isn't
different.
it like max of the absolute values?
Sir,
yes.
Sir, in ridge regression, you write here as a plus lambda by 2 W transpose W, but W transpose W is square. Actually, that will be square of second norm, sir, not second norm. W
You're right. Square of
W
second.
will be, yes, sir, yes, yes.
So W transpose W is so okay. So W transpose W would be W0 square plus W1 square plus W2 square up to W M square, which is W transpose W, and which is also square of second degree norm square of this quantity. You're right. If I had put a square root like this, then we would have norm second norm of W, but now I have to put a square to get rid of the square root. You're right.
Yes, sir. Yes.
So please make note of that. They are not same. And you are taking, if you are taking square root of this, not necessarily you are going to get this quantity.
Yeah. Yes, sir. Thank you for this, sir. Otherwise, I probably would have made a mistake tomorrow.
Okay. All right. Any questions? Any further questions?
Sir, what did you tell in just last? I just missed it.
So W1 norm of, first norm of any vector, let's say X, is defined as this: sigma of xi, which is individual component of the vector, mod of it as equal to 1 to m, assuming that it has m number of components. Second norm of any vector is defined as this: again I is equal to 1 to m xi square and then square root. So second norm is also equivalent to Euclidean distance. Okay.
Okay, sir, clear. Thank you.
Sure. Now the last point which is remaining for this is the how would you choose the best lambda or regularization rate? If you if lambda is very large, let's say it tends to infinity, what is going to happen? If it tends to 0, it is going to happen. 0, what is going to happen? And lambda, which is the best, how do we find it? Okay, so if you look at the equation, I think this is last part. We are coming to the end of regression part of week 3. So if lambda goes to infinite, so what it is saying is, I don't want to increase the W's at all. I'm giving it too much penalty. If it is very strict, then I should write it here. As lambda tends to infinity, W tends to 0. Okay, and as lambda tends to 0, that means there is no penalty, right? Then W goes to the solution of least square.
How, sir, how W goes to 0 when lambda tends to infinity?
Right. So what you want to do is, yeah, somebody wants to say?
Yes, I asked Rosina.
Okay. So imagine that if lambda is tending towards infinity, that means you are giving it very high penalty. You don't. So what will happen is this quantity is becoming very large. So what is the, and we want to reduce the loss function, right?
Yeah.
Then how would optimization procedure is going to reduce this quantity, given that there is a large penalty over here, there is large number over here.
Okay, then W should be 0.
Right. It is going to make W tending towards 0.
Okay.
Okay. And the last question is, how do we find the best or optimal value of lambda? So we don't know beforehand. So what we do is we do the experimentation with it. So we plot the cross validation loss, okay, with different values of lambda. And the chart might come something like this. And we choose the value for which the cross validation loss is smallest. And that is our best value of lambda for that model.
This cross-validation loss is basically just loss on the validation data set, or is it RMSC? What does that mean?
So cross-validation loss, okay. So let's say we divide the data set into, let's say, 4 parts, 1, 2, 3, and 4. So these 3 will be used for training. This will be used for validation. Okay.
Yes.
Okay. So and similarly, we are going to run it one more time. Actually, few more number of times. These 3 will become, let's say, training. This will become validation. Similarly, let's say this time this become validation. Remaining become training. And similarly, this become training. Validation. Others become training. Okay. So we are going to repeat this procedure and compute the loss for all validation folds. Since we are doing four-way cross validation, therefore we are going to get 4 values of losses, right?
For each lambda.
For each lambda, of course.
Right.
And what we do is we average this, and this becomes our cross validation score or cross validation loss. Okay. Okay. And for every value of lambda, we plot this cross validation loss as this chart. Okay, and so for whatever value of lambda, we are going to get least cross validation loss is the perfect or the chosen value for our model or best regularization rate.
So cross validation, this curve basically tells us that this is the ideal training set for which we have an equivalent validation set. That's what this is trying to say, is it?
No, it's not trying to say that.
Because we are training on different combinations of training data set, and then we are validating against that validation set, right?
Right.
So the lowest validation loss, cross validation loss, will occur when the training set is most representative of the model that can help me reduce the loss on my validation set. Is that fair to say?
Can you repeat that part?
So what I'm saying is, see, we are trying to first train the model on different training sets, which is the different combinations of training sets. And then we are calculating the loss for each of the validation set for different validation sets within the same batch. So my understanding is that the loss will be minimum when the training set is the most representative, that particular training set which is most representative, that can give us a model that will reduce the validation loss in the validation set.
You're right. You're right.
No, sir. I think the cross-valid, that's my understanding. I may be completely wrong. But my understanding is that if we take a single split, suppose you've taken the first example, and you have got 3 training and 1 validation, that may not be an ideal measurement of loss, because you may get a validation set which may or may not be the ideal representation.
That is true. That's why we use cross.
So that's why we take more representation. So we change the validation set every time and average it out.
Absolutely.
We also take the standard deviation to see if there's not much change. That is done in the practice course, but generally we change the training set every time so that we get an average and we say, okay, this is more representative of the loss.
Right.
My understanding is that that's why we take cross validation.
Right. Absolutely right. So the possibility of having training set and validation set differing in their distribution and causing our model to be poorly prepared or poorly trained, we take one fold at a time for validation set and rest of them for training, and then repeat this procedure for every fold, so that every sample gets a chance to become training sample as well as validation sample.
And this is just the loss calculation, right? Not the RMS.
We can compute loss as RMC, right?
Okay, so now I'm just wanted to confirm whether cross validation loss is the loss or the RMSE, or can be any.
So cross validation loss, we can use RMSE or SSE, both of them.
Okay. Okay.
Sir,
yes.
This cross validation data is used for the tuning of the hyperparameters.
Yes, absolutely.
So, sir, my question means, sir, suppose we train our model and reduce our losses, and then at the end we tune the hyperparameters. Is it?
No. So hyperparameter tuning. No. So see, for every set of hyperparameters, what you do is you do the complete training process, right? And note down your loss. Then you do the same thing for the next set of parameters, and you keep doing this for all possible combinations of hyperparameters are exhausted, and then choose the model for which, or choose the hyperparameters for which the training loss or validation loss was smallest. Does it make sense?
Couldn't get 100% means confidently.
Okay. So let's say you don't know the degree also. You don't know what will be the best degree for this. 2, 3, 4, and 5. These 4 values you choose. And for lambda, you choose, let's say, 10 to the power -5, 10 to the power -4, 10 to the power -3, and 10 to the power -2. So let's say you decide that these you want to experiment with these hyperparameters. Right? There are 2 hyperparameters. The degree as well. Okay, put 1 over here also, and let's say put 10 to the power -1 as well. So 5 each. So what would you want to do is you want to experiment with all combinations of this. So you take degrees equal to 1, right? And for all values of lambda, you do this.
Yes,
okay.
Yes, sir.
And for this, you note down the model, best model of degree 1. You do the same thing. Degree 2, all possible values of lambda. You choose the best model out of those. Degree 3. And you keep doing this for all possible combinations of your hyperparameters. You choose, and among this grid, you choose the model which gives you the least cross-validation error. Does it make sense?
Yes, sir. Yes, sir. Okay. Means, sir, this will work in the grid search only.
This is basically grid search. This is your grid.
Yeah.
Right?
Yeah.
5 and 5 elements over there. So 5 by 5 is your grid.
Yes, sir. Yes, sir. Okay. Thank you, sir.
Okay. Any questions so far?
Sir, here one question. Like
yes.
in one of the graded 3, there are question asked, the 14th question. Rajesh has a nonlinear data generated from a sine 2 pi x function where 0 less than equal to x less than equal to 1 with the 50 samples. So in those options, like how can we make sure like this will be smooth fit or this will be under fit basically?
Okay, can you point me to the, it's week 3, right? Which question?
Yes. Graded assignment 3, question number 14.
Give me one more, I'll bring it up.
Question number 14 as well as question number 9. So where this type of question comes, yeah, you can take first question number 9. That is also the same function sine 2 pi x.
Okay. So consider, okay, I'm going to share my screen.
Yeah.
Okay, so this is how it looks like. Consider that you have some nonlinear data generated from sine pi x function. The polynomial regression model of higher degree, say 8, adds a smooth fitting to nonlinear data when there are large samples, say 1000. Okay, polynomial regression model of higher degree, say 8, forfeits nonlinear data when there are large samples, say 1000. Okay. The polynomial regression model of lower degree, say 1, adds a smooth fitting to nonlinear data. So this third one outright looks wrong. Fourth one, polynomial regression model of lower degree, say 1, underfits nonlinear data when there are large samples of 1000. This also looks wrong.
How that's a higher like that overfit option looks wrong? I mean, I'm not getting
Okay, so the answer says polynomial regression model of higher degree 8 overfits.
So actually, if you increase the training data, the model will fit better.
Right. So that's one way
but
to.
Since the degree is high, so it will overfit.
And the data samples are small.
So if you take large samples and the degree is high, then it will tend to overfit the data.
Large number of samples or large samples?
Large number of samples. I think it means large number. That's what it means. But large.
Higher degree here, the degree is also high.
Okay. By the way, it's given 0 belongs from 0 to 0. So sine 2 pi x, if x is varying from 0 to 1, it's basically one complete oscillation, right?
Yeah.
Okay. So sorry, I should have read that first. 8, say, adds a smooth fitting non-linear data and there are large number of samples. Right, so first one doesn't make sense. If the data is non-linear, no, it should.
We need to choose the incorrect statement.
Right. So that's why second one should be wrong.
Then why the first one looks correct? How? I mean, why it is like smooth fitting?
Good point. So there are a couple of ways to handle overfitting. One way is to add more number of samples. The second method is regularization.
Okay, but here the number of samples is high. With that, degree is also high.
That's true.
So
if
the degree is high, then model will be complex and it becomes like overfit, right?
You're right, but if you provide sufficient number of samples to your model, it will not be able to overfit.
Okay, then I mean, by such questions, how will we know like this will be the sufficient number of samples?
You have to imagine, right? This is a general question. It's not like that. For answering this question, you have to write a program and do experiments. You have to just go with the intuition.
Okay.
Sir,
Yes.
before you could change the screen, I mean, there's another question in practice assignment 3, the number 1.
In the same.
Give me one. Practice assignment 3, question number
1, sir, the first one.
Okay.
Sir, in this, I couldn't understand how it is being said that the linear regression model with so-and-so degree underfits the data when I compare the values between the trained RMSE and validation RMSE.
Right. Okay, good question. So, if you, this is exactly, this kind of situation is exactly represented by the graph that we just saw some time back. So, this one. So your training loss is consistently decreasing, but your validation loss looks something like this.
Okay, but if you see the data there given, it isn't anywhere close, though it is increasing after a certain point. So I pick that point and fix it. Is it, sir? I mean, it isn't close though to the training error.
Okay, am I audible?
Yeah, you are, sir.
Actually, for the underfitting, both should be high. So in the
right.
Yeah.
So look at the point for which validation loss is minimum. I think it is for degree 4, right?
Yeah. Yes, sir.
So relative to that, degree 0, 1, 2, 3 are definitely underfitting. Relative to 4 again, 4, 5, 6, 7, 5, 6, 7, 8 are overfitting.
So we just look at the validation and then kind of predict it.
Yes. Also look at training error. It should be consistently decreasing.
Reducing. Okay. Got it, sir. Yeah. Thanks a lot. Thank you.
All right.
So yes. Question number 14 in the same assignment, graded assignment 3.
Okay. Last question is this much. Okay.
Yeah.
Choose the statements which are true. This is the one, right?
Yes, correct.
Okay. So, which one of these statements are supposed to be true? Okay. So I would guess that imagine a function which represents this equation, which should be x squared plus bx plus c form.
Okay.
Right. And see if the model, again, go with the intuition. As the regularization rate increases, if it is too large, then what happens is your model starts to underfit, right?
Mm-hmm.
And if regularization rate is too small, then it starts to overfit.
Okay, so why, how can we say the option C is incorrect? Only option is correct. How can we say only option B is correct but not option C?
Okay.
So B is difficult to judge. The last one we can say that model with that is okay too. But 0.01, I agree with her. It's very difficult to judge without using the collab.
I agree with you. Yeah, I totally agree with you. So this one definitely, to properly answer it, you have to use collab. So rest assured, this kind of questions will not be there in the if you are wondering about that.
Okay, sir. Thank you.
Sir, I have a doubt. In
Sure.
polynomial regression, if we are given like five number of elements, and we have to calculate degree 3, is there any formula to calculate how many elements will be there in the degree 3 set?
Yeah. So degree 3, you count all the features for degree 1, 2, and 3 and sum them up.
Is there any direct formula for that? I was asking.
You can derive. Yes.
Okay, sir, I'll look into it.
Okay. So now I'll not take any further questions. I'll allow Nitin to continue the revision sessions, and at the end, we will take all the questions from week 1 to week 4. Hello, Nitin.
Yeah.
Please proceed.
Yes. Thanks. Good evening, everyone. Let's start with week 4. Up to week 3, we have seen regression problem, and week 4 is about classification problem. So let me share my screen first. So can you see my screen? Is my screen visible?
Yes, sir.
Yes, sir.
Okay. So week 4 is all about the classification problem. Here we will learn linear models. In linear model, we will please mute yourself. Okay. So here we will have two linear models. One is square classification model, and second is perceptron model. Both are linear models. So we'll see how these models look like. So first of all, just an introduction about the classification. So you know the difference between classification and regression very well. In the regressions, the the labels are continuous variables. Whereas in the classification problem, the labels are categorical variable. It means they are classes, they are categories. So that's the difference between regression and classification problem. Both are supervised learning algorithm. So our task is to take an input vector and to assign one of the k classes. So if there are k classes, to assign that particular example to one of those k classes. This is our goal in the classification problem. So how to achieve this? We are going to see all this problem here. So before that, if there are m feature, then input space is going to be m dimensional space, and so those examples, those data points will be distributed over those m dimensional space. And our target is to find decision boundaries such that those boundaries can separate those classes, those k classes. Okay, so if there are k classes, we have to divide our input feature space into k different spaces, k different parts. Okay, so this is our target here. So there are different ways in which we can learn those decision boundaries. Depending upon the model, there are of two types. One is generative and discriminative model. Second is discriminative function. In the generative and discriminative model, we learn the probabilities of y given x. We learn the probabilities y given x using Bayes theorem in the generative classifiers. For example, Snipe Bayes classifier that we're gonna learn in the next week's other week, 6 week or 7 week. And next is discriminative classifier. Again, here you learn the probabilities distribution p by given x, but using some parameter models like you have done in logical regression or SVM models. In the second type, discriminant functions, here rather than learning the conditional probabilities, we try to learn the functions that similarly to that we have done in the regression problem, but we can say that the discriminant functions or linear classification problems are actually motivated from regression problem as well. So what is discriminant function? Discriminant function is just a function which takes an input vectors and assign one of those k classes that is called a discriminant function. It actually is a hyperplane, m-1 dimensional hyperplane in m dimensional space. There are m features. Okay, so let's jump to our actual data set. If the data is there are n samples, n features, then the data matrix is gonna be look like n of the shape n cross n, and the label vector depending upon the problem. Let's see how the label vector will look like, label vector or label matrix. For a single level classification problem, it means each and every example is associated with one and only one label. So that is single level classification problem. So for n example, there will be n such outputs, and our label vector is gonna look like something like that, by 1, by 2, by n, where by each by I is the label associated with ith example. So what is one-hot encoding? When we do one-hot encoding, let's say your one example, consider an example which belongs to class I. There are k classes, and that example belongs to class I. So for that particular example, the one-hot encoding gonna be like it's just a vector whose ith entry is 1, and all other entries are 0. So it is one-hot encoding of that particular example. So for n examples, we are gonna write the encoded vector here as a rows. So in that manner, we will get an encoded matrix of size n cross k, because if there are k classes, so the k columns will be there and n rows for each example. This is for single level classification problem. For multi-level classification problem, each and every examples may have more than one level, right? So let's say there are k classes. So that by is gonna be look like 1, 2, 3 up to p classes. So it will be 0 for if let's say by has the labels 2 and k. So the corresponding level will be 1, and all other entries will be 0. So your label matrix is gonna be look like of size n cross k, where k is the number of classes and another number of examples. So here in week 4, we are gonna see the discriminant functions to separate our different classes. So what is discriminant function? Is just a function that takes the input. It's just a linear combinations of the features. So if you look at this W0 plus W1 x1 up to W, this is gonna be Wm, not m. So plus Wm xn equal to 0. This is gonna be it's hyperplane in m-dimensional hyperspace. In other manner, you can also write W0 plus W transpose x, where W0 is the bias or intercept and W is the weight vector. So what is the geometrical interpretations of this discriminant function? So this interpretation gonna help you to understand the model. So keep these 4 points in mind whenever you are trying to understand the model. So first is pretty easy, that this discriminant function is m-dimensional hyperplane in m-dimensional feature space. Second, for a given x, the value W0 plus W transpose size is actually the distance of that point from the decision surface, that plane or hyperplane. Okay. Here, in this is discriminant functions, this W0 actually decides the location of the decision surface. So how it decides? The proof is easy. If you see that discriminant functions, it looks like W0 plus W transpose x. So just manipulations here, W naught upon norm of W equal to, so this is your distance of the hyperplane from the origin. So if you see that W0 upon norm of W is gonna give you the normal distance of the hyperplane from the origin. So in that sense, you can say that the W0 determines the location of the decision surface. So this is very important point here. The next is also important. W vector W actually this.
Hello, sir.
Someone saying something?
Yes, sir. Can you explain these two formulas with a simple example, sir? It would be really helpful.
Which formulas?
Distance formula. Yes, sir. With the quiz question only, you can do that, sir.
Okay, give me 1 minute. Give me 1 minute.
Okay, sir.
Can you see the whiteboard?
Yes, sir. Yes, sir.
So your decisions, our hyperplane is gonna be W0 plus W1 x1 plus up to Wm xm equal to 0, right? So this is your hyperplane in n-dimensional space. If you have to find the distance of this hyperplane from the origin, then it is gonna be W0 upon norm of W, right? So what is this? Let's say for a particular example, your surface is 3 plus 1.5 x1 plus 3 x2, something like that. 5 x3 equal to 0. This is your hyperplane, and you need to find the distance of this surface from the origin. So it is gonna be W naught. W naught is 3 upon norm of W. So what is norm of W? This is 3 square plus 1.5 square plus 3 square plus 4 square and root over this, right? So this is norm of W. So this is your distance of the hyperplane from of a hyperplane from the origin.
So
Okay, what is the next?
Is the W0 also included while taking the norm? Because if you do this calculation for the quiz paper, you won't get the right answer. For the mock paper. Mock.
Okay. So
in that W0 is not
formula?
included. Yeah, the same formula. In that the W0 is not included. So it's only W1 up to Wm which is included.
W0 is like the bias, right? Is the
Sir, I can
yeah.
tell you the quiz
Actually,
question.
yeah, W0 won't be included there. Yeah, you are correct. Yeah, you are correct. W0 won't be included there.
Yeah.
Remember
also,
by mx plus c, right? Or say ax plus by plus c equal to 0. So distance is what? Distance is simply c upon root over a square plus b square, right?
Yes, sir.
Same kind of thing is this. This is a plane in 2 dimensions, right?
Sir, how would we? There is another.
It's a line. It's a line in a 2-dimensional space, and the line itself is a 1-dimensional space. So you can compare these things. This is your W0. This is your W1 x1. This is your W2 x2. This formula you have seen in the MES 1 course or MES 2 course, right? So if you got confused with these notations, remember these things. So here distance is c upon root over a square plus b square. So c is not included here. That is W naught is not included here. And remember, we have used the notations W0 separately and W transpose X separately. So here we are talking about norm of this W. So we are not including W naught there. Hello.
Yes, sir. Also, sir, there is another question wherein they give a point, and from that you have to find the hyperplane distance. How would we do that? We have to substitute that point into this equation, is it?
Yeah. So that value is gonna give you the distance from that surface of that point from that surface.
And then
that's gonna be a sign distance
divided by the norm of W, right, sir?
No. There you need not to divide the distance. The value itself.
Sir, I can just probably give you that question itself. It says there is a line that passes through the origin, and it is along the direction of the weight vector 2, 2, and there is a point 10, 0.1.
Okay.
So they're asking us to find the distance from that 10, 0.1 to this line, which is in the direction of 2, 2.
Okay.
So how do we go about
the line is passing through point of, so
yeah, line is passing through 2,
point 2, 2
via the origin,
and,
through the origin.
And what are other information is given?
And the point is 10, 0.1.
10, 0.1.
So they're asking for the distance from this 10, 0.1 to the line that is passing along the direction of the weight vector.
So this thing, right?
Correct. So that's the weight vector, direction of the weight vector. Yeah.
Somewhere here. So this distance we always consider as a distance of the point from the line, from the plane. Yeah. So you can find the equation of this line, right? So 2, 2. So this is actually by equal to x, right? 2, 2, 0, 0. So it is by equal to x line. So you can say x minus y equal to 0. Understand? Now from this is from this point, so the point is 10 comma minus 0.1. So from here you can find the distance.
I am not very clear about how to find the distance though. I got the equation, but
the answer is not correct.
Yeah, because the thing is, even if I do the projection approach, then also the answers comes out to be very different to what is given. So I'm not.
So you are talking about the
I verified.
Previous question. So which question is this?
So this was one of the quizzes in the last term or something like that.
You mean the
so,
okay.
Not the mock, but it was the actually quiz paper last term or something. Last term or the
even in the mock, there is a similar question.
Similar question, yeah.
Okay. So what is the answer given there?
In the previous quiz for this particular question, it was 0.65 or something. 0.65 to 0.68 was the tolerance, was the answer given. And whatever I try and do, I'm not getting 0.65. I'm getting 7 and that kind of number. Even if I do projection and other types of methods, I don't know how 0.65 came about, but that's part of a quiz paper.
Sir, in this also, do I do ax plus by plus c divided by root of a square plus b square? Is that the formula that I do?
Yeah. Okay, yeah. Ax plus by plus c upon norm of a. I mean the a square plus b square. This should be the right answer. This formula should give you the right answer.
Sir, I tried this question by the 3-4 method, but the answer was coming the 7 point something. Whatever the answer was given, that 0.61 to 65.
Yeah, that answer I saw in discourse 0.65 na. Previous year's answer, it was wrong. The answer was wrong.
What is the answer given? 0.65.
0.61 to 0.65 is the given answer, but that answer is wrong.
This is definitely wrong. This is very low value.
Okay, so the best way to approach it is so in this case ax plus by plus c is what in this case?
Ax plus by plus c is what means what?
I mean, what is that equation?
Kaushik, that is the equation x minus y. So you substitute whatever x
so
and y
here,
we've
here
given.
In this case, yes. So here in this case, it is x minus y equal to 0, right? And your a is 1, b is 1, c is 0. So it is going to be 10 minus 0.1 upon root over 1 plus 1. So root over 2. So this is 9.9 by root over 2. So what is this value?
Something 7 point something.
So this is the right answer. This should be the right. I will cross check as well in the quiz. Is the mock right? You're talking about or the last term quiz.
This was I mean this specific number was last quiz, but I think there is a similar question in mock also, but different numbers.
Okay, last. Okay. I'll check that. And if I told something wrong here, I will post that in the discourse. I think this should be the correct answer. This should be the correct approach for this.
Okay, sir. Thank you.
Okay. So let's go ahead.
And just out of curiosity, I mean, I don't know if it is applicable. So the one approach I tried was projecting that 10.01 onto that line, which is on the vector. So finding where it intersects and then calculates the distance. That is also a right approach, right? I'm getting the same one.
Yeah.
Yes.
Obviously.
Okay.
And I think the formula came from that approach as well. This formula, I'm not sure, but that formula comes from that approach only.
Okay.
So remember this thing, W0 decides determine. Yes.
So the formula which you used for the finding the distance, but there the point was not coming into the picture. Means from which point we are calculating the distance?
No. You have to put those. Your formula is ax plus by plus c equal upon norm of that parameters. I mean that coefficient c square plus b square, right? So here you have to put that x is 10 and y equal to 0.
Okay.
Those points.
Okay.
There will be mod symbol in the top, sir. In the numerator,
Sorry?
mod symbol will be there, sir.
Yeah, no, this one. Okay, distance. If you are considering sign distance, then you can avoid this absolute part. Okay, sign will decide whether it is upper side of the plane or lower side of the plane. Okay.
Yeah, got it, sir. Got it. Yes, sir. Thank you so much, sir.
So next thing is the vector W actually decides the orientations of the decision surface. So here, similar kind of thing, right? You have seen this in the math lectures as well, right? So right, that simple line. Let's say this line. So x minus y equal to 0, not x minus y, x plus y equal to something, right? X plus y equal to 5. So here, what is your a and b? So W vector is gonna be 1, 1, right? And if I change this 1 minus 1, so 1 minus 1 will give you x minus y equal to 0, equal to something, or if it is 0, c is 0, then it is something like that. So your W vector actually deciding the orientations of your surface. If it is something like parallel to this, so some W vector will come like 1, 0, right? Sorry, by equal to constant, so it's gonna be 0, 1, something like that. So actually W vectors here your decides the orientations of that hyperplane. Okay, so the proof is also easy for that. You can see. Okay, so here the proof is given. Let's consider 2 points x1 and x2 on the decision surface. As they are on the decision surface, so values of that corresponding to those points on the surface gonna be 0. So these two equations will give you 0. If you use these two equations or subtract these two equations, you will get W transpose multiplied by x1 minus x2 equal to 0. So remember the again. So W a dot b equal to 0 means that a and b are orthogonal to each other. So here vector W is orthogonal to the vector x1 minus x2. So x1 minus x2 is actually a vector lying along with the line, right? Lying in the line. So it means that W transpose is orthogonal to the line, to the hypersurface. Okay, so in that sense, because it's always gonna be normal, so W transpose is gonna decide your orientation of the decision surface. Okay, so this is a typical in the two-dimensional hyperplane. If there are two features x1 and x2, your hyperplane is gonna be one-dimensional. That is a line. So here normal distance of the plane from the origin gonna be W0 upon norm of W. And for any particular point x, here x is given. So this distance is gonna be y divided by norm of W. Okay. So remember this gonna give you the sign distance. We are not considering the absolute part. So if it is positive, if it is y is positive, then we are on the upper side of the hyperplane. And if y is negative, then we are on the lower side of the hyperplane. Okay, so this idea we can use to actually predict our class level. So we will just simply check the values of a given example using the hyperplane, and we'll check whether that value is positive or negative. So if the positive, it means that we are on the upper side of the plane, and the values is negative, then we are on the lower side of the plane. So on the upper side, we can say it is a class 0 or class 1, whatever the points are, whatever the class is there, and the other way, and 0 class in the lower side. Okay, so this we can use to predict our values, predict our classes. Is line 1D or 2D? So line is always one dimensional. Okay, so space is 2-dimensional, but the line, the hyperplane itself is the line is 1-dimensional, not 2-dimensional. Okay, so this is all about the data set and discriminant function. So always keep these 2 points, that what actually W0 gives you, what W gives you. So it will help you to understand the model. Okay, so let's move to the model now. First, we will consider least square classification model, and the next we will consider the perceptron model. So both are linear in nature because they are actually the discriminant function is the linear combinations of the features. So both of them are the linear models. So consider situations where the key classes classification problem is given to you. Now apply the linear regression approach to that model. Yes.
Sir, your voice is too low. I can't hear you.
Is it for everyone? Hello.
Yes, sir, it's too low.
Is it fine now? Hello.
No, sir. The same, sir.
Is it fine now?
No, sir.
Give me 1 minute. I just rejoin and maybe the problem is with my connection. So is it fine now? Hello.
Yes, Nitin.
Is it fine, Chandy, now?
Nitin, your screen is not visible.
Yeah. That I have to. I cannot share it now. Just give me 1 minute. But my voice is okay.
Yes, sir.
Yes.
So, yes, so we were talking about the model for least square classification problem. So here what we consider our simplest model is just a linear combination of the features. So our model for K classes classification problem, we are gonna form K discriminant functions, and whether we are gonna check for which discriminant functions value is greater. So if it is greater for yk for all such discriminant functions, if it is greater than for yk, then we will classify that example to the class K. Okay, so for binary classification problem, and one more thing here, decision surface, that the surface that is gonna separate different classes, that decision surface for class I and class J is gonna be by I equal to by J. So let's say for decision surface that separates class 2 and class 3, it is gonna be the by 2 equal to by 3. I mean the difference of these two, W20 minus W30 and W21 minus W31 x1, something up to W2m minus W3m xm equal to 0. So that surface, that hyperplane is gonna be the decision surface or separating surface between class 2 and class 3. So for any two classes, decision boundary between any two classes is given by I equal to by J. Okay, so for binary classification problem, actually we need not to find two different discriminant functions. We actually can have one discriminant functions, and if it is greater than and for decision for predicting the class labels, so if it is greater than 0, then we will predict into the class positive class, and if it is negative, the value is negative, then we will predict that example into the negative class, or say 0 class 0 class. Now for K class classification problem, once we have found the values using K discriminant functions and predict the values, now our target is to, so for first just see the notations here. So this is the decision surface between class K and J. And for two class classification problem, we can simply write it as W0 plus W transpose X equal to 0. We need not to find two discriminant functions. We can use both the methods, but it's gonna be the same. Now, our notation is gonna be for K, we have K such discriminant functions, and we can write as X into W, where X is of the size n cross m plus 1, and W of the size m plus 1 cross K. Right. So W has actually all those m plus 1 into K parameters. Remember, for one discriminant functions there are m plus 1 parameters, and there are total such K discriminant functions. So actually it learns m plus 1 into K parameters at a time. So the shape of W is gonna be m plus 1 cross K, where each row represents the values. So each column represents the values, parameter values for first discriminant function, second is all the discriminant functions. So zeroth column will give you all the parameters of the first or say zeroth discriminant functions, and the last column will give you the parameters of the last discriminant functions. So how you will make predictions. So I just told you for you just check the values for all K discriminant functions, and if it is greater than for ith discriminant function, we predict into the class I. So actually for that matrix, we will check for which index, for which column it is maximum, and we will predict into that class. So it is actually the max of XW. XW is gonna give you the values of those values of those functions, discriminant functions. And if it is maximum for class I, we will discriminant function I, then we will classify into the class I. So this is how typically, let's say for three classes R, I, RJ, RK. So this is how your decision surface is gonna look like. So these three red lines are actually the this is by I minus by J. This line is gonna be by I minus by K, and this line is gonna be by J minus by K equal to 0. And what are by I, by J? These are three different discriminant functions corresponding to region I, J, and K. And this line actually shows you that any decision surface, any input space that that partitions actually it's connected. So for any 2 points taken in that partition, any points joining those points is always gonna be inside that region. So that region is connected. Every partition is gonna be connected. Okay, so this is model. Next is loss function. So how your loss function is look like? So error is gonna be given by actual predictions. Sorry, not prediction. Actual labels minus xw. So this is your gonna be predictions. So this is your error. So error transpose error. The trace of this matrix. Remember this by here. It is the encoded matrix, and this is again gonna be of the size n cross k. So this is of n cross k size, and the trace of that matrix is gonna be your loss function.
Sorry, so just a quick question. So just to understand this, the predict function is going to give you the class which has the highest probability, right?
Yeah,
I mean, highest value.
Gonna give you the class.
It will give me the
predict function the class.
Okay. Now the class could be 0, 1, 2, 3. Right? I mean, because if it's argmax, and if I have, let's say, 5 classes, it can go from 0, 1, 2, 3, 4, right? But when I do label encoding for 4 classes, that will be like 0, 0, 0, 0, 1 or something like that, right? It will be either 0 or 1, depending on which element I am in.
Okay.
So I'm just trying to see, you can predict really be compared with the Y label, the output of predict, which is giving me the argmax.
Okay.
Can that be compared with the label that we have after hot encoding, after encoding? This is where I'm getting. Does argmax give me either 1 or 0? I mean, I'm just trying to understand if I have 5 classes. So there will be, and let's say I have 3 weight vectors, then I'll have 3 by 5, 5 by 3 discriminant functions, right?
Okay. So your doubt is whether the output can be converted into the encoded matrix, encoded vector.
Yeah, can it be compared like that?
Yeah, because let's say your class is 0. If it is there, it predict to be class 3. So you actually can convert into the encoded vector. So encoded vector is gonna be look like 0, 0 and 0, 0, 0, 1.
Yeah, so which means I have to encode what comes out of this predict function, is what you're saying, for me to compare. I can't directly compare argmax
with
just
predictions. You need not once you have defined x into w, so you have to predict which example it belongs to, right? Which class it belongs to. So if you have seen it, just say it is in class 3. So it is enough to make prediction. You need not to convert into the encoded matrix. Vector.
So what we do is we actually convert that label back into, that is why we do this decoding or whatever. We convert it back into the label without encoding and then compare it, is it? Because see, normally I think in all the typical processes that we have seen, we compare the output of predict with the output of y label vector. That is how we normally do, right?
Yeah.
So in this case, argmax is going to give me an
here
index.
Remember,
yeah, sorry.
Okay, just give me 1 minute. I just explain what you are saying. So remember here, x is of safe. So x is of safe n cross m plus 1, right? And w is of the same m plus 1 cross k. Right, so your x into w is gonna give you the matrix of safe n cross k. So here this index, this value actually give you the value corresponding to that discriminant functions. So you have k discriminant functions, w0 plus w01 x1 plus up to w0 m xm, right? So this is your first discriminant function. Second discriminant function w1, first discriminant function w011 x1 up to w1m x1 equal to 0. So this is your second discriminant function. Up to you have k discriminant function wk plus wk1 x1 plus wkm xm equal to 0. So xw actually these values. Okay, so for
and the
very
predict
first
function
example,
gives,
so very
sorry, go on.
example, so let's say you have example x1, x2, x3, three examples. So first examples have, so corresponding to that we will calculate these k values. So all these k values will go here. All k values will go here. Okay. Sorry, just read it incorrectly. All k values will go here. K labels are there, right? K columns are there. So all k values will go there for first example, and there are such n examples, right? So discriminant values for first example is this. Discriminant values for the second example is all these k entries, and discriminant values for last example, the nth example, is these k values. Okay, so what we actually do, we just check which for which discriminant functions value is maximum, right? So what np.argmax will do of xw, we are checking. So it will check along the each and every row which index is maximum. So it is checking for which discriminant functions the value is maximum. So if it is maximum for, let's say, second 0, 1, 2, second, will predict example belongs to class 2. For nth row, if it is maximum for the class k, then we will consider that the nth examples we will predict that nth example belongs to class k. Right?
Right.
It is just the matrix notations of whatever we have seen in the model.
Yeah. So this I understood. So now it will be
what.
Yeah, so this will now turn out to be 2, 3, 4, whatever, and k will be the vector, right? Now, if I compare this to y, which is encoded.
You are seeing that encoded, right? So let's say your prediction, your actual classes are class 0, class 1, class 1, class 2, something like that. 4 examples are there, and your encoded vector will look like 1, 0. So 3 classes are there. So 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, right?
Correct.
And let's say your predictions are something like that. It is class 0, it is class 1, it is class 2, it is class 2, right? So this is your prediction. So you can compare easily. So and here you can see it is class 0, it is class 0, it is correctly predicted. So this is class 1 actually, and predicted to be class 1. So it is again correctly predicted. Here it is class 1 actually, and it is predicted to be in the class 2. So it is incorrectly predicted, right? Similarly, for the last example, it is correctly predicted. So you can compare. You can convert this to
back
this.
And then
you can convert. You can you can decode this, or you can encode this, or whatever you want to do to compare it.
Okay. Okay, sir. Thank you.
Okay, so next is loss function. Loss is given by the actual labels minus xw. So this is your predicted matrix. So this is your error corresponding to all those examples, and so error transpose error. So trace of this matrix is gonna be the loss function. Okay.
So again, in this case, y here will be in not the encoded form, sir.
No, this is encoded form. Look at the matrix n cross k.
Okay, and xw will be in whatever is the output of xw. That's all.
Yeah, xw. We are not predicting here. We are just finding the values of xw.
Okay, but then how can you subtract it? Because
so we are actually finding the cost corresponding to each. No, both are in the same dimension. Y is n cross k, and x into w is gonna again is n cross k.
Okay.
So the next part is the optimization, which discriminant function is going to be the optimal values, optimal model. So again, there are two methods: normal equations and the normal equation means that you just take the derivative of the loss function and equate it to the 0. So if you find the derivative of this function, so derivative of loss function of with respect to w is actually x transpose xw minus y. So if you equate this equal to 0 and find the value of W, it is gonna be X transpose X inverse X transpose Y. So this is you find the weight vector using the normal equation. Second is iterative. Again, the same thing. You take the steps in the directions of local minima or global minima, and how to take the steps. It is decided by the parameter alpha here. So the same kind of thing we have already seen in the regression problem as well, right? So any problem up to here, the loss function and optimization. Okay, so next part is evaluations. For evaluation, we can find accuracy, precision, recall, or F1 score. Any of these things will work. So what is accuracy? How to define the accuracy?
So you take the true positive and true negative and divide it by all the true positive plus true negative plus false positive plus false negative.
So accuracy actually give you how many are correctly predicted, right? Out of total, how many are? So fraction of those which are correctly predicted. So true positive and true negative gonna be in the numerator, and denominator all those examples in the training set. Sorry, in the test set. And for precision, what is precision?
So it's true positive by false positive plus true positive.
So precise means what? How many they are correctly?
How many of the predictions were correct? How many of
out of those which are out of those which are predicted positive are actually positive, right? So true positive upon how many are correctly positive, predicted positive, that is true positive TP plus false negative predicted positive. So that gonna be your FP, right? Falsely predicted positive. Okay. And what is recall?
Recall, we take the actual in the denominator. So what is how many of the predicted was
actual
the proportion of the actual.
Yeah. So out of those which are positive, predicted to be positive, right? So that is gonna be recall. And what is F1 score? It is just the geometric mean of not the geometric harmonic mean. So F1 score is gonna be the harmonic mean of precision and recall. Okay. So any of these you can use for the evaluation part. So any problem in this model, Discriminative classification problem? Okay, so let's jump to the next model, which is Perceptron model. Give me.
Or any questions from week 1 to week 4 altogether?
Okay, so should I start with Perceptron?
Yes, sir.
Sure.
Okay, so again, training set we have already seen it is linear model. So training data, it's again the same. So how is the model? So again, we take the linear combinations of the features and then followed by a nonlinear activation function. So here nonlinear activation function is if it is greater than 0, it's class 1, and it is less than 0, -1. So what is Z? It is again linear combinations of the features. So same thing, linear combination will give you the distance of that point. So positive means that we are on the upper side of the plane. So if we are on the upper side of the plane, we predict it to be class 1. And if we are on the lower side of the plane, we predict into the class -1. So this is your activation function look like. We generally call it the sign function or the threshold function. Okay, so here we are also considering the phi x means the polynomial transformations of features. You can also think, you can just visualize our linear transformation, need not to do polynomial transformation. Okay, so this is how your model look like. And next is loss function. So you just in the loss function, you simply just check whether they are correctly predicted or not. So if they are correctly predicted, it means if by hat equal to by, then the error corresponding to that example is 0. And if it not correctly classified, it means if by hat is not equal to by, then the error associated with it's gonna be W transpose phi of xi, that is linear combinations multiplied by the actual label and the minus sign of this. So if you notice this thing, if you verify this thing, it actually gives you the positive quantity, because if linear combination is negative and incorrectly classified, and so by is gonna be positive, so negative gonna be positive, and if linear combination is positive, then the actual level is actually negative. So again, this gonna give you the positive quantity. So error, this is gonna be the error associated with that example, that incorrectly classified example. And so this function can be rewrite as this thing, max of 0 of minus of this thing. So these two are the same thing, just different notations for this. So what gonna be the total error? So total error gonna be the sum of error for all such examples, of all n examples. So actually, if you remember, yeah, so this is gonna be your error function, loss function for the perceptron model.
And just to be absolutely to confirm, so the loss function is going to return, if it is misclassified, it will return some real number, right? Not just one or 0, because this is going to be a linear combination of
This function gonna give you, that's what I'm thinking. In some, I think in the slides I've seen that you can define as the h of I mean that signal function of this linear combination, right? Then in that case, it will give you the 1 or 0. So
or the
in
count,
that case,
right? Count of misclassification.
The loss is gonna be total number count of misclassified points, misclassified examples.
Okay, so in case in the exams we are asked to calculate the loss, what do we do? I mean, do we calculate the real number, so the actual value, or should we do the number of misclassifications? Because I think in the implementation also it is taking misclassifications.
Yeah, number of misclassification points.
Okay.
Okay. So if you look at the loss function here, so here on the x-axis we have taken the linear combination multiplied by the actual labels, and here is the loss. So if you remember, this is this is of the kind max of something 0 and minus of x, right? Because on the x-axis you have this thing. So this is the graph of max of 0 minus of x. So this is how your loss function will look like.
Sir, here one question: why Z like that loss function is not differentiable in W? Because W term is still there, right?
Look at the form of ZW. It is of max of 0 of something, right?
Yeah.
0 of that parameter, that x. You can think it is x. So how you will differentiate with respect to s this function? This is not differentiable function. Max of this, max of something is not a differentiable function.
Okay.
Right. So JW is not a differentiable function in W.
Okay, sir, got it. Okay. Thank you.
So main part is here how to optimize this procedure. because JW is not differentiable in this case. So we cannot use both the methods, normal methods and obviously that stochastic gradient descent. I mean the gradient descent we cannot use because JW is not differentiable anymore here in this case. So what is the procedure here? Because before moving to that, remember those points. W0 gives you the distance from the origin, and vector W gives the direct orientations of the hyperplane. So if we make changes in the W, so idea is just randomly initialize your W vectors. Let's say you have randomly chosen W0 to be 0 vector. Now idea is you have to move those vectors, those hyperplane in such a manner you just check the values of the loss and corresponding to those to minimize those loss, you just move your hyperplane in that manner that it minimizes your loss. In other sense, it actually try to classify the misclassified point correctly. Okay, so in that manner we will gonna find the optimal hyperplane. So remember those points that if we change the W vector, the orientation vector orientation of the hyperplane will change. Okay, so we will check which points is misclassified. In that direction, we will try to in that direction we add the W vector so that the plane orientation will be in such a way that it will try to classify that misclassified point in the correct class. Okay, so this is your optimization procedure. So you randomly initialize your vector. Here we are initializing with a 0 vector, and you just check whether the points each and every example you just check whether they are correctly classified or not. So if they are correctly classified, you just you just check the predicted value here, and in that you how to update the weight vectors in the tth vector tth iteration if the vector is W. So in the t+1 iteration, your updation gonna be WT plus alpha times by I minus by height I and phi of xi. So if they are correctly predicted, this term gonna be 0, right? If they are correctly predicted, they gonna be 0. So you are not updating that corresponding to that example. So if that example is incorrectly classified, then you just keep adding that linear combinations that point to that weight vector. So your weight vector changes and the orientation of the hyperplane changes in that direction. Okay, so that is the idea behind the optimization procedure of a perceptron model. You just keep on rotating your hyperplane, moving hyperplane in manner that you try to minimize your loss. Okay, error. And two more points in the perceptron model. Perceptron only works for the binary classification problem. Second, if the data is not linearly separable, then perceptron model will not converge. Okay, so keep these 2 points in mind as well. For more than 4 multi-class classification problem, you cannot use perceptron model, and for non-linear separable data, the perceptron model will not converge. So you have to by yourself you have to set your number of iterations ahead of the time for that model, but the loss will not be 0 anyway. So this is all about the perceptron model. Any questions here?
Sir, can you please solve a couple of questions which can be asked in exam from week 4?
Which can be asked in week 4?
Week 4, yeah.
No,
this one.
So if you have solved mock paper, if you've seen last term quiz paper, so same kind of question gonna be there in quiz paper.
Sir, actually solution is, sir, if possible, can you please share the solution of mock test?
So tomorrow is the exam, right?
Yes. So that's
before that is not gonna be possible, but we'll try to post it later. But before tomorrow is not.
Yeah, because sir, why any graded or PA assignment solution is not attached? Like only answers is given. So like we don't have that much time as a professional. I just go through the concepts, and because lectures and the videos are also not so good, so it is very difficult if some question, because in theory we can't cover the questions, so no question is I have found solved in detail. So That's why we are struggling here.
Hello, Rosine, I would like to add a point. So for week 3 and week 4, completely solved practice and graded assignments have been shared. They will be soon shared on the portal, but as of now, the link is available on Discord. Let me write it in this post, in this chat box. Will that work for you?
Yeah, that is fine. And if is mock test solution is also available for you, if you can share in the chat or somewhere, that would be really helpful.
Okay, let me take a look at for that also.
Sure, sir. Thank you very much.
So there was something about the regions of in one versus rest and one versus one, etc., given in the slides. If you could explain that, that is not very clear to me on how that is coming up.
Yeah, so there are two different ways to say techniques or different ways to find this classification for Lister classification problem. So one is let's say there are K classification problem, right? So one way is to 1 versus 1. So for all such pairs, you find discriminant functions and make classifications, and and other way is 1 versus rest. So 1 versus rest means you will take 1 and versus all versus K minus 1 other K minus 1 classes. So you will find the discriminant functions for 1 versus all and check whether it is in class 1 or other class or not. Class 1 or not in class 1.
Sir, I understand the formula
So
as in K minus.
there are some ambiguous things.
There are some images which are given in the slides. That is what I don't understand, sir.
Okay. Just let me open those images, then it will be better to make understand.
Yeah. Yes, sir.
Just give me one. Okay, so here in 1 versus rest, let's say you have 3 classes, class 1, 2, and 3. So corresponding to that, you will find 1 versus rest. So in 1 versus rest, you will find 1 versus C, 1 versus not C1. I mean 1 versus C, R1 and R2, and C2 versus not C2. So let's say this is your discriminant functions or hyperplane for 1 C1 and not C1, and this is the hyperplane corresponding to C2 and not C2. Now look at this region. For this hyperplane, this says it is the region C2, right? For this hyperplane. Now again, yes. For this hyperplane, this is the region C1. So this is kind of ambiguous region because this hyperplane says that this is the region C. This is the region C2 region, and this hyperplane says that this is the region C1. So this is ambiguous region.
Okay, since it falls in both the hyperplanes, sir, that is the ambiguous one.
Both the places. So that's why this is the ambiguous region.
Okay. R3 is not ambiguous because both are not C1 and C2, is it? We are saying R3 is not ambiguous because
now look at the region R3. So this is not C1, not C2. So this region gonna be R3. So there is no ambiguity here. Similarly for this one. So this one for this hyperplane it is C1, right? And for this hyperplane it is not C2.
Okay. R3 will come that it's something like a class 3.
Sorry?
The region R3, it is not C1 and not C2, right?
Yes.
So will that come out to be R3. A third class?
Yeah, this is third class.
Okay. That is why it is not ambiguous, correct?
Yeah. Only this green region in the ambiguous. Okay. So 1 versus 1. So similarly, 3 classes R1, 1 class 1, class 2, class 3. Let's say for 1 versus 1. So you will find the hyperplane corresponding to 1 versus 2, 1 versus 3, 2 versus 3. Okay. So 1 versus 1. Let's say this hyperplane is for 1 versus 3. This hyperplane is 1 versus 3. So this is C1, this is C3. This horizontal hyperplane is for C1 versus C2. So this region is C1, this region is C2. For this hyperplane is for C2 versus C3. So this is for C2 and C3. Now look at this region. For this hyperplane, this is C2. For this hyperplane, this is C1. And for this hyperplane, this is C3. Right? So this is kind of ambiguous region here.
Okay, so basically, sir, wherever all these 3 intersect or 2 or 3 intersect, that is basically the ambiguity region.
Yeah.
Okay, got it.
It looks more like it is ambiguous when all the 3 are true.
Yeah, together.
Yeah, if it is all the 3 are false, then it is not ambiguous.
Yeah, if you are able to make correct, you are able to make predictions, then it is not ambiguous. So here, look at this region, R1 region. For this plane, this is C1. It says this is C1. For this hyperplane, it says this is C1. So this is, and again for this hyperplane, right?
Yeah.
C1, C1. Okay.
So you're not audible. I think you're saying something.
Hello.
Yes, sir. Now you're audible. Sir, again, it's gone.
Hello. No, I'm not speaking that. So R1 we are talking about, right?
Yeah. Yes, sir.
So R1 is the decision surface for C1, is it? So anyone to the left of R1?
This is region for C1, class 1. And surface is this one. So this surface, this decision surface is for class, whether class C1 or C2. So decision surface for class 1 and class 2.
Oh, I thought it was each line represents whether it is C1, not C1, C2, not C2, and C3, not C3.
No, each line decides if these line separates those classes. So these lines are actually the discriminant functions. So here in this case, 1 versus 1, we will find k minus 1 by 2. I mean you have to find pairs, right? How many pairs you can make? So NC2 pairs you can make. So here k minus 1 divided by 2 pairs you can make. So for 3 classes you will make 3C2. That is 3 discriminant functions you will find.
Okay.
Okay.
Yeah. Yes, sir. Thank you, sir.
Yeah. Okay. So any other questions?
So one general question, I think a couple of questions in the mock came from pandas, whereas we haven't used pandas much as such in this one. Knowledge on pandas, yeah, knowledge on pandas, some basic question on pandas only. But I don't think we've used pandas much extensively in this course, at least in theory, in techniques. So I just wanted to know if we need to brush up pandas for... in the mock had some questions on pandas.
So Kaushik, I believe the questions must be really basic ones. How to load the data set and which format, whether in a data frame format or a bunch format and things like that, I assume. Is that correct?
No, so there were some questions on the functions as well, like iLock and such things.
I see. So yeah, they are still under the fundamentals of using pandas. So accessing
Actually-
rows, columns, and particular entries that could be good to brush up.
So actually, we done pandas data frame, but this is panda series. The question is based on panda series. So we'll need to brush that up also. Or is it the
I would
same?
suggest. I would suggest them brush them up briefly, like in half an hour or so. Not to go in details.
Right.
Okay.
One more suggestion is please go through NumPy, because there, as you must have seen in the mock also, there are code blocks which make use of NumPy, and then there are questions or options based on that code block.
Sure. Yeah, NumPy, I mean, I understood NumPy is certainly important. Just that pandas, we didn't use at least things like series much in the techniques course.
And so NumPys, there is a week 0 which gives a lot about NumPys. So NumPys, I think, is okay. It's the pandas which is not actually, we are not well versed with that.
Okay. So I would suggest not to spend too much time of it, just brush up quickly.
Okay, sir.
Any further questions? Okay. Then I think we can close it now.
Yeah, thank you, sir. And sorry for holding you up.
Not at all. Actually, we are happy that you stayed this long. It's more than 2 hours.
Yeah.
3 hours actually. Yeah.
Thank you, sir.
It was very useful. Very useful.
Hello, Swanim sir. Can you please share the mock solution?
Okay, Rosina. So by the way, I'll look for it. But I would suggest that if you have worked on the practice and graded solutions on your own this term, then you don't have to worry about it. I'm pretty sure that
I'm struggling with the week 4 basically, so I'll need definitely a solution for those questions because I'm currently on week 4.
Okay, sure. So did you find the link that I shared in the chat box?
Yes, that is for week 3 and week 4, right? But that is like I haven't solved week 4 activity questions. I can solve practice and graded.
Okay.
But I have found like in WhatsApp chats also people are struggling with the mock assignment. So
I
like,
see.
no one is 100% sure about it. Like how to solve it basically.
Okay. Okay, Rosina, I'll look for it.
So sir, how will you share it because tomorrow is an exam? So how you are gonna share it?
So I would request you to look for the discourse. I'll post in discourse because I'll post in both places. I'll try to post in the portal as well as in discourse so that whichever students visit first, they can get it from there.
Okay, and sir, till when can we expect this?
Today is Saturday, so I'll try to do it as soon as possible. When is your quiz starting tomorrow?
Tomorrow by 10:30 we have to leave from home because exam center is almost 35 kilometers away from here, from my place.
I see. Okay, Rosina, I'll look for it. I cannot say by when, but I'll definitely look for it.
But sir, definitely please make it before quiz at least. Otherwise, it will be not be so helpful.
Okay.
Yeah. Okay, sir. Thank you.
Thank you.
Thank you so much.
Thank you, everyone. All the best. I'm pretty sure that you will do great. You stayed this long. I'm pretty confident you are going to get high scores.
Thank you so much.
Thank you.
Thanks for all the efforts from the team. Thank you.
Thank you, everyone. Thanks, Nitin. We should drop off now. Good night.
Best of luck.
Good night, sir.